In the last couple of videos, we've been looking at 2x2 contingency tables and estimating the magnitude of association between the two categorical variables using relative risk or odds ratios. In this video, we're going to continue to look at contingency tables with two categorical variables, but instead we're going to look at it from the perspective of a hypothesis test. So to illustrate, let's take a look at some data, and this is for an experiment to learn more about a particular type of parasite that part of its life cycle it is in fish, and then the fish can be eaten by birds, and then the parasite gets transferred to the birds, and that's one part of the life cycle of this particular parasite. And so this particular experiment, let's actually take a look at the data, and then I'll explain a little more clearly what's going on. So here's the data. So one of the categorical variables is to do with the status of the fish. And so we've got fish that are uninfected by this parasite, fish that are lightly infected by the parasite, and fish that are highly infected by the parasite. So there's three levels for this categorical variable to do with the infection status. And then some of those fish get eaten by birds, and some of the fish are not eaten by birds in this particular experiment. And so this is our other categorical variable, the fate of the parasite. And so what we're interested in is whether the infection status, or let me put it this way around, what we're interested in is whether the chance of the fish being eaten by a bird or not, whether that is dependent on the infection status of the fish. So in other words, is it the case that, for example, the more highly infected the fish, the greater the chance that it's going to be eaten by a bird, and because of the way the life cycle of this particular parasite works, that's advantageous for this particular parasite, because that means it moves on in its life cycle and continues to evolve. So what I did here was, before I actually created this table, I skipped over this, but I'll return to it now so it's clear what I did. Anytime we have a categorical variable like this, so we've got this categorical variable, infection status, and this one, the fate of the fish, whether it gets eaten or not. And the way that, I've mentioned this before in a previous video, but the way that R orders the categories in a categorical variable, the default ordering is alphabetical. And that isn't necessarily the most meaningful from a researcher's point of view. So in this particular experiment, it makes sense to order the categories of the infection status. If we make uninfected the first category, lightly infected the second category, and highly infected the third category, we're going to get more meaningful pictures of the data. Whereas the default ordering would be, let's see, it would be highly first, and then lightly second, and then uninfected third. And so in this case, we want to switch the ordering. And why I want to do that, maybe that'll become clearer if I actually draw a mosaic plot of the data. So the reason I wanted to do that was because this gives a nice visual representation of the data here. So we've got infection status as the categories along the horizontal axis, and they're ordered according to the order that I just defined. So uninfected on the left, and then lightly infected in the middle, and then highly infected on the right. And so the reason I wanted to order it in this way here is because we could think of infection status as increasing from left to right, which is more sensible than having it go the other way. Okay, so we're going from uninfected, lightly infected to highly infected as we increase along this axis. And then on the other axis, we've got the fate of the worm inside the fish. Is the fish eaten by a bird, or does it not be eaten? And so we can see here that the uninfected fish, there's not many of those that get eaten by birds. Whereas the lightly infected fish, there's a bigger proportion that gets eaten by birds, and then the highly infected fish, there's a whole bunch of those that get eaten. And so it looks like there's some kind of biological mechanism here where the more highly infected the fish is, the more likely it is to be eaten. And so that's the message that we're getting from this graph, but we want to test that empirically. And so we're going to have we're going to do a hypothesis test to confirm whether this sample data indicates that there is a dependence between infection status and the fate of the fish, or the fate of the worm inside the fish. So that's what we're going to do next, is do a hypothesis test. And it turns out that the hypothesis test that we're going to use it's essentially a chi-squared goodness of fit test. So we considered chi-squared goodness of fit tests in a couple of different contexts already in this lesson. We looked at a chi-squared goodness of fit test for frequency data, and then we looked at a chi-squared goodness of fit test for Poisson data. And so now this is a third application of a chi-squared goodness of fit test, but it applies specifically to contingency tables, and in particular it's generally known as an independence test. So as usual, we've got 4 steps to go through when we do a hypothesis test, and the first step here is to state the null and the alternative hypothesis. And the null hypothesis here is that the 2 categorical variables are independent. So in particular, parasite infection and being eaten are independent, and then the alternative is that those 2 categorical variables are not independent. So parasite infection and being eaten are not independent is the alternative hypothesis. And just looking at the data in the mosaic plot, it looks like the data is going to favor the alternative hypothesis in this case, because it looks like these 2 categorical variables are not independent, because the likelihood of being eaten seems to depend on the infection status. There's an increase in the proportion of fish that are being eaten as the infection status changes. So let's see if the data and the hypothesis test actually confirm that suspicion that we have. So we've done the first step. We've set up the hypotheses. The second step is to calculate the test statistic. Okay, and because this is a chi-squared test, we know how to do that. Okay, what we do is we look at the observed frequencies in the let's go back down here in this table. So these are the observed frequencies, and we could also calculate expected frequencies if the null hypothesis was true. So if the null hypothesis was true and the 2 categorical variables were independent, we would be able to calculate the expected frequencies. And so rather than going through the details of how to calculate those expected frequencies, we're going to rely on the chi-squared test function. So that's going to do all the calculations for us, and we won't have to worry about doing hand calculations and possibly making mistakes. So one of the advantages of R is that there's lots of built-in functions like this that will do all those calculations for you without you having to worry about remembering formulas and doing long, complicated calculations. So we'll run the chi-squared test, and then we can just look at the what it comes up with. So of course the observed frequencies are just going to replicate the data. Okay, so that's what the observed frequencies are, and then it's telling us the expected frequencies, and these are the expected frequencies if the null hypothesis was true. So if the infection status and whether or not the fish gets eaten, if those two variables were independent, this is what we would expect for the frequencies. And then we know how to calculate the chi-squared test statistic because we take the difference between the observed and the expected, we square that difference, and then we divide by the expected, and then we do that for each cell in the table, so there'll be 6 of those in this case, and then we add those quantities up, and that gives us the chi-squared test statistic. And we can look at that chi-squared test statistic here, and it comes to 69.756. So that's the second step, calculating the test statistic. The third step is to calculate the p-value, which is the probability of observing a test statistic as extreme as the one we got, or even more extreme. And for that we need to know what kind of chi-square distribution to use, so we need to know what the degrees of freedom should be. So the degrees of freedom for this chi-squared independence test, what we do is we count the number of categories for one of the categorical variables. So there's 1, 2, 3 categories for the first categorical variable, and then we subtract 1, so 3 minus 1 comes to 2, and then we look at the number of categories for the other categorical variable, so 2, and again we subtract 1, so 2 minus 1 comes to 1, and then we multiply those two numbers together. So we multiply 2 by 1 and we get 2. So that's the degrees of freedom for the chi-square distribution. We don't have to worry about actually calculating that in this case because R figures it out for us, and it figures it out correctly. So it tells us that the degrees of freedom is 2 for this example. And then the p-value will be the upper tail area to the right of the test statistic for this particular chi-square distribution, and it tells us that that p-value is a really tiny number, 7.1 times 10 to the minus 16. It's, for all intents and purposes, 0. So that's step 3, and then step 4 is to make a decision and draw a conclusion. Our decision rule is always the same. Reject the null hypothesis in favor of the alternative hypothesis if the p-value is less than the significance level 0.05. And this number is, as I said, is essentially 0, so it's certainly less than 0.05. So we reject the null hypothesis in favor of the alternative. And the alternative hypothesis here was that parasite infection and being eaten are not independent. And does that confirm what we saw in the picture? It does, because when we looked at the mosaic plot of the data, we could see that it's strongly indicative of whether or not the fish gets eaten is highly dependent on the infection status of the fish. So this hypothesis test and this p-value essentially 0 confirms that visual impression that we were getting from the mosaic plot. So that's how to do a chi-squared contingency test, or it's more commonly known as an independence test.